All right, good afternoon. Okay, there's only 3 of you, so you really kind of have to respond. I was throwing up on the screen here the where we're at, where we're headed, so I'll show that real quick. Hi, Kelly. I see you in Paducah.
Hello.
And so today is, if you can believe it, we're in week 3 already of the semester, right? Of basically a 16-week semester, almost a fourth of the way through. And so what we're going to do today is we're going to cover the second lecture from chapter 3. And then Thursday we'll cover the third lecture from chapter 3. And then next Tuesday we'll have the exam review, and then you'll have an exam on that following Thursday. And it'll be over chapters 1, 2, and 3, and the goal chapters 1 through 20. I may revise that to 1 through 15, kind of depending on where we get with discussion questions, kind of a thing. So that being said, let's go ahead and take a few minutes and talk about the goal, okay? So we'll start with 1 through 5. Has everybody read chapters 1 through 5? Has anybody read 6 through 10? No? Okay, so you guys just have stopped it. Kelly, I didn't see you nod, but they nodded here that they've just done 1 through 5. So that's what we'll cover here today. And part of it is, the discussion is not, I'm not going to tell you that you're right, you're wrong, right? But what I want is for you to think about these things, and then as you progress through the book, I think some of how you think about some of this might change, okay? So let's just talk about this. Unico is the name of the company that Alex works for, right? And so they have these stacks of this order, and I'm going to go ahead and take it off the screen because I don't think you can really read that much off of the screen anyway. But they have stacks of this particular part, right, waiting on another part for final assembly. So from your perspective, is that good or bad? So kind of in agreement that that's bad. And why do you think that? I'm going to start. We'll just start with Eric, and then we'll kind of work our way.
Because they're waiting, they're not being processed.
Right. So anytime we kind of have inventory in a pile someplace without anything happening to it, it can be a bad thing. Okay. And I say can be because you've probably heard me say before, inventory is a tool, and there is a time and a place where you need to use that tool. But if it's there without a specific reason, then it's probably not going to be a good thing. Okay. So then, Katie. The issue of efficiencies comes up several times in these chapters. And so when you think about efficiency, how would you measure efficiency? And do you think it's an important metric of management? Just verbally describe what you think of.
In the book?
Yeah. Or just generally, what do you think of when we talk about efficiency?
The fastest way to make something and produce something, but it won't.
Okay. So, and if you guys would, probably you'll need to use the microphones or Kelly won't be able to hear you. So, yeah, if you wouldn't mind doing that again.
Efficiency would be like the fastest and most efficient way to produce something.
And for the lowest cost, right? So that's kind of, efficiency gets at doing it at the lowest cost, okay? And so do you think of efficiency as an important metric for management? Okay, I think we can agree that it is. I think that that'll be one of the things, though, that as you continue to read, it's going to challenge your perception of efficiency. So not necessarily what you just said, but I want you to be aware as you continue to read, and have they talked about the robots yet and how they produce more?
I don't think so. It was like 2 weeks ago.
Yeah, so it's been a bit since you've read it. So one of the things that they talk about is, you know, they have new technology, right? And Alex is going to try to present to, what's the name of the guru that he's trying to meet with? I can't think of his name now.
The head guy in that meeting he was at?
So, okay, you're not there yet. Okay, so we haven't met this guy that he's going to go to for advice, okay? So just be aware that when they start to talk about efficiency, the fact that the robots produce more, if the robots produce more, it's not necessarily efficient unless you're reducing things in other areas, right? So if you produce more inventories just so you can store more inventory, that's not really efficiency, right? And so think about efficiency from the way that we normally think about it, and then think about it in the context that they kind of transition to, okay? So again, there's no right or wrong answers here. We're just kind of talking through what they're looking for. So Kelly, out on the floor, a reel of shiny steel slowly unrolls into the machine that every few seconds says ka-chunk. Why might that be important? Do you have any feel or flavor for why that would be important?
To me, it's saying it's not working properly.
Okay, because it's making too much noise?
Yes.
Okay, so I think that could be a concern. How about you guys? What did the ka-chunk mean to you? Did it have any, did it?
Before that, you said, did it say it continuously cuts it? What you said?
So out on the floor, a reel of shiny steel slowly unrolls into the machine that every few seconds says ka-chunk.
We're probably cutting it before they need it.
Okay, so they're probably cutting it before they need it. Okay, I think that's a good insight. Okay. I think maybe the ka-chunk part of it is probably every time it's actually making a cut. So you can think of that ka-chunk as the pace that is actually working at too, right? And so I think the noise is a concern, because you'd always be, wonder, okay, is that normal or not normal? But then when you hear that, that's the pace that particular work center is working at, right? And so I think they want you to be aware, think about the speed that those work centers are working at. Okay? And then it says on pages 14 and 15, there is a concern expressed over the inefficiency of people hand-carrying subassemblies one at a time from one production station to the next. And is that efficient? And is that efficient or inefficient? And are they losing economies of scale? So think about this. You've got people that are having to pick up and hand carry stuff. Does that seem to you at this point as it's efficient or inefficient? Eric? Yeah.
That seems pretty inefficient to me that they have to carry them by hand one by one.
Okay. All right. So, and then what do we say that they're losing? I think you could safely say they're losing economies of scale by doing that, right? So really, just to kind of help you frame this up, what they're doing is they're setting up kind of the traditional way that we think about efficiencies and economies of scale. And then what Alex is going to do through his consultation is they're going to start to challenge some of those assumptions. So really, all we're trying to do here is just kind of set up that that's how we think of these things, right? And so just make sure that you're open as you start to read some of the different things that, well, maybe the traditional way that we think about these things, maybe there's room for some other ways to think about it, okay? So, yeah, one of Rogo's departments enjoyed a 36% improvement in productivity due to robots. Okay? So do you think that matters? Katie, do you think that matters, that 36% improvement?
It sounds like it matters, but then again, it depends if you're wanting more robots or like more employees.
Okay.
Because you'd have to cut them if you have more robots, I feel like.
Okay. All right. So that 36% improvement in productivity for robots, I want you to keep that in mind, because that seems like, they're hanging their hat on that. They're really proud of the fact that they've got this efficiency in this department, okay? And so I think that's again, the traditional way that we think about things is what's a particular department doing, okay? So it's Jonah. That's the name of the guy that he consults with, right? So, so according to Jonah, productivity is the act of bringing a company closer to its goal. So Kelly, do you agree with that?
Yes and no.
Okay. You always have the MBA answer. That it depends. Okay, so go ahead and tell us why you think yes and no.
Well, I think yes if your production is going efficiently.
Okay.
Makes sense?
Okay.
But then if you've got it inventory sitting in one spot for too long, then no.
Okay. All right. So Jonah would say that, what does Jonah say the goal of every company is? Eric, do you remember?
To make money?
Yeah, so he says the goal is to make money. So his question, I think, would be, does the 36% increase in productivity at the robots, did that help the company make more money? So the question would be, if it did, right, they would have had to sell more product to customers, right? Or they would have had to have less labor in the plant, right? So something has to give in order for that to actually be an improvement, okay? And so that's kind of what they're trying to get at is, I can have these robots do it a lot faster maybe, but if them doing it faster isn't the bottleneck of my process, it's not really helping anything. Maybe that system that was going ka-chunk is as fast as we can do anything, because that's as fast as what we can get something done. And if I'm going 100 miles an hour over at this workstation, but I can only go this fast at a bottleneck workstation, this is not helping me any, right? Because that workstation that goes slower and is at that ka-chunk pace is probably going to be where I have a bottleneck. And that's part of what we're going to look at with Little's Law, is trying to find those bottlenecks. Okay? All right. I'm kind of flying through these. I'm not hitting every question, but I think this is an interesting observation. So with respect to the brilliant idiots in purchasing, Alex comments, they're out there renting warehouses to store all the crap that they're buying so cost effectively, right? So then, is that really cost effective? If you have to buy it, you might buy it at a reduced price, but if the storage costs, and I think it's that it depends, Kelly, that'd be a good answer for you, right? It depends on whether or not the storage costs are less than the actual savings that you're going to achieve, okay? And so, again, just kind of as you start to read, so you should be reading chapters 6 through 10 this week, and we'll hit on that next week, okay? Kind of keep that in mind about this approach in terms of looking at where they're actually going to find the issues in the facility, okay? All right, so I think that kind of gets us through the first 5 chapters there. And with that said, I want to go ahead and move into chapter 3, and we're going to start to use Little's Law in some interesting ways in chapter 3. So let me bring up the PowerPoint that I want to use there. And I'll flip back to the PC. So this is going to be the second lecture out of chapter 3. And it's the fundamental kind of how we start to piece together how we're going to use Little's Law. So you all probably did your homework from last week. Did you have any trouble with that? Did that go pretty straightforward? Okay. Yeah. Good. Good. They were meant to. So always glad when things come together. All right. So this week we're just going to start to add a little bit of a broader vision and a little bit of complexity to what we're working with. Okay. And so we've done the goal. We did the first 5 chapters rather than the first 10. You said you finished the 3A homework without too much trouble. And so today we're going to talk about how operational measures link to financial measures. We're going to talk about Little's Law in terms of a linear process in both a simple and a multi-step. So again, we're going to go do the very basics and just consider this a building block kind of approach. And so each lecture kind of builds on the previous one. And then we're going to use, again, I thought this was really interesting the first time I did this, these financial statements to analyze financial flows. And I think it's interesting that the level of information you're able to pull out if we think about how we can put this information together. Okay? So, operations management, process analysis, and applications module. So, we're going to work on using Little's Law, and if we remember, T stands for time, I stands for inventory, and R stands for throughput rate. And I typically shorten it to throughput, but if it helps you remember that R is throughput rate, then tack on the rate at the end of it, okay? And again, at the end of the day, we're going to talk about some levers for improvement in terms of how this might come together. Okay, so it may seem fairly obvious to those of us that are logistics and supply chain majors, but it's not always obvious to everyone. How can operations be a source of competitive advantage? Okay, and historically, what we would say is that in the 1960s and before, we'd say the low cost and scale economies is how we can do that. So the Model T example, you can have any color you want as long as it's black, right? We're going to produce it and you're going to buy it. And that's the way it goes, okay? In the mid-1960s, we transitioned into something called focused factories, where organizations would have the standard product in one and then the custom product in another factory. And you try to keep those separate because what you're competing on is different in those factories, right? Remember we talked about in the first couple chapters, cost, quality, delivery, flexibility, innovation, right? So you kind of separate those factories. And then we moved into flexible factories and product variety, where we kind of bring it back together, but technology allows us to do that. A car for every taste and purse, right? You can buy a new car from $10,000 to, I don't even want to guess what the most expensive one would be, right? And then in the 1980s, we moved into the quality is free movement, the Philip Crosby kind of approach. And then in the 80s and 90s, okay, we love your product, but where is it? We started to not be able to meet customer demand with the very specific things that they were looking for. So don't sell what you produce what sells, right? And so then it's a matter of kind of backing into it and trying to make sure that what's coming off the end of your production line has already been assigned to a customer and saying, well, that's what they want, okay? So again, after World War II, that approach was kind of, if we build it, they'll buy it. And then we got behind Japan in the quality revolution. And so some of the top quality gurus started in the United States, but because we couldn't get on board with that movement, they moved to Japan. Okay, Deming is one of those. Again, you've had in 343, we talked about the quality movement, and so you have some information from that, from Management 350, I'm sure, from Marketing 360. So I don't spend a lot of time kind of rehashing that, but just know, I mean, that's a key element here. Okay, and so then when we start to talk about how do we create economic value, right? Well, we take that kind of relationship on the top where we talk about profit, right? And we say the difference between profit is revenue and costs. Well, revenue is made up of price and quantity, and costs are made up of the material costs, labor costs, energy costs, and overhead costs. Okay. And on the bottom, we have our opportunity costs, where we talk about the capital invested times the weighted average cost of capital. That's a way to look at that. But the improvement lever is all the way over on the right-hand side, right? In order to how operational levers can improve financial measures. Well, if we increase the price, right, we're probably going to sell more. If we increase the throughput, if we produce more that we can sell, we're going to increase the revenues, right? If we reduce costs on the production line, right, that's going to add to the profit. And if we improve quality, that's also going to add to the profit. How does improving quality add to the profit? How do you think that's going to impact the bottom line?
We're going to buy that over something that's made crappy.
Okay, so they're going to want to buy that over something that's made crappy. Okay, what about on the production line? What does improved quality do for a production line? So think about this. What happens if I have bad quality? What do I have to do? If I find it on a production line, what do I have to do? Okay, you want to use your mic so Kelly can hear? Sorry.
Maintenance to try and fix the issue to get better quality.
Okay, so, and you might have to set the unit off to the side, right? You have to might come back and rework it, right? So all of those things are going to add to the cost. So if you can have better quality, you're going to improve that throughput at those workstations, and that's going to actually lower costs as well. And then if we are able to do more with the same equipment, right, we're going to reduce our capital intensity. We're not going to have to have as much money invested in capital. One of the things when we did project planning at Pella, which I found interesting, was they would actually give you credit on projects for floor space saved, right? And so that's a sunk cost for them, right? They've already produced a facility, okay? But their perspective on it was that unless we encourage you to be efficient with your use of space, you're going to spread out, and we're going to have to build more plants, right? And so if you want a project to go through, if you can show us how that's going to reduce space, we're going to give you some financial credit for that in terms of prioritizing the project as a go or no-go, because in the long term, we have to build less factories if we're efficient with our space utilization, right? And not all companies will look at it that way, but some will. And so it's an interesting, piece of the puzzle when you're trying to promote a particular project. And then reducing inventory, right? If you've got, so when I was the supply chain manager at Pella here in Murray, my perspective, and it's changed a little bit over the years, but there are people who are very focused on reducing inventory, right? My predecessor at the plant, that was what he thought he lived and died by, okay? But the problem with that is, and I think I've shared with you before, is he ran the production lines out of inventory, and they couldn't produce during the week, and they'd have to come in on the weekend and finish up their production runs, right? That's hell on morale, right? And if you have to expedite stuff in, right, you really aren't gaining that much. And so I always used to think about it as, well, it's really whatever the interest rate is. Because if we've made an investment in inventory, right, if I have to pay interest on that money, let's say we've borrowed that money, so that's really the cost of holding that inventory. It's a little bit more than that, because there's an opportunity cost that if you've got it invested in inventory, you can't invest it someplace else, right? But it's also a tool, and so you're trying to use that tool to balance things out. But generally speaking, reducing the inventory is going to improve your profitability because you're going to move things through the system faster. You're going to get dollars back into the organization faster, right? If I have 1,000 units in inventory and I have first in, first out, it's going to be, 1,000 units have to flow through before I'm ever even going to get that unit to the customer. And they're going to think about paying me for that unit. If I have 500 units, I've now cut in half the time since I finish a unit until it gets to the customer, and we're actually going to bill the customer for the unit, right? And so that reducing the inventory can be important that way as well. Okay. So back to last class, we have flow time, throughput, and inventory, right? Those are some key operational performance measures. We also talk about process cost and quality. So flow time, again, going back to last class, is the total time spent by a flow unit within the process boundaries. If we draw that box around the process from the time it enters until it exits the process. Throughput is the average number of units that flow through the process for a given period of time, or throughput rate. Okay? Inventory is if we took a snapshot in time and we said how many units are inside the process at that snapshot. Okay? So oftentimes if we're actually trying to count that in a process, we will take an average. We'll go out and we'll take a snapshot 10 different times. And we'll take the average of those 10 and we'll say that's what our inventory is. Okay? And then process cost has to do with, well, what's our material cost? What's our labor cost? What's our energy? What's our overhead? And then quality gurus would say, and rightfully so, that improving quality reduces the total system cost. Okay? So we're going to do a very simple linear process, and you'll see it drawn across the bottom. And so across the bottom, the triangle represents a buffer, and then we have a register activity, another buffer, and then an intern. So the example is at a hospital emergency room, patients come in at the rate of 20 per hour. Okay? At the rate of 20 per hour. Katie, inventory, throughput, or flow time? 20 per hour. Throughput, right. Okay? And they're processed at that rate as well, which just tells us the stable process. Okay? And patients wait in queue until they are called in for registration. After registration, patients are taken to an inner area where they are assigned a bed, where they wait till an intern is ready to see them. On average, it is found that there are 30 patients waiting for registration and 20 waiting to be seen by an intern. So Kelly, when we say 30 patients and 20 patients, are we talking inventory, throughput, or flow time?
Inventory.
You got it. Okay. And then on average, it takes a patient a quarter of an hour in the registration process and 3/4 of an hour with the intern. So Eric, what are we talking there? Inventory, throughput, or flow time?
Flow time?
There you go. So we've been given some information about each of these steps. Okay. And so what we want to do is we want to transfer that information into a table. Okay? And so you can see I've still got the diagram across the top. And inside the triangles, I put the amount of inventory that we were told is at each of those triangles, right? And so we were told that we have 20 patients at buffer 1, and we have 30 patients at buffer 2. We were told that our throughput is 20 patients per hour. And what that means is that along each of these arrows, you're basically saying that you have 20 patients per hour flowing through that process, okay? And then for the activities, we were given the amount of time that it takes to do each activity, right? And we say it's at roughly a quarter of an hour to register and 3/4 of an hour to meet with the intern, okay? And the first year I taught this, I didn't set up the tables and we just tried to talk through it. And I'm just here to tell you, setting up the tables organizes it in your mind and makes it really clear to see what 2 out of 3 pieces of information you have. Because in order to solve these problems, right, you have to know the 2 out of 3 pieces of information, okay? Because we know Little's law says inventory is equal to throughput times flow time. So if we know 2 of those 3, we can solve for the third, okay? And so that being said, we're just going to transfer into the table then. What we know is across every step, we have 20 patients per hour. So my throughput in a linear process, and that's an important piece of the puzzle, in a linear process, every patient flows through every step. So my throughput is exactly the same across every step. So we have 20 patients per hour, okay? And then in my buffers, right, I know that I have 20 patients of inventory and 30 patients in inventory at each of those buffers. And at each of those steps, I know that I have a quarter hour at registration and 3/4 of an hour at the intern step. Well, this makes it pretty clear, right? At buffers, I can calculate flow time, right? And at inventory, I can calculate the inventory, or excuse me, at action steps, I can calculate the inventory because I have both throughput and flow time. So the way that I typically set it up, and I'm just going to repeat it so for a little time here, is when you have a linear process, so one in which every flow unit goes through every step of the process, input your throughput across every throughput cell in your table, okay, all the way down through the total, right? And then wherever you are given the time of an activity, input the time in your table, and wherever you're given the number of flow units, input the flow units within that step, or input the inventory, okay? So that's what we were provided in this problem, and now I could solve, and I almost always include this row with the formulas just to keep me honest. Inventory is equal to throughput times flow time. Throughput is equal to inventory divided by flow time, and flow time is equal to inventory divided by throughput. So to calculate flow time for buffer 1, 20 divided by 20 is going to be 1, right? 30 divided by 20 is going to be 1.5, okay? And so I'm going to run those calculations, right? So now what's in purple is what we've calculated. So we calculated the flow times at each of these, and we can calculate the inventory at each of these activity steps. So inventory is equal to throughput times flow time, so 20 times 0.25 is 5. So that tells me that on average I have 5 patients at registration in that step of the process. And at the intern, I have 20 times 0.75, so I have 15 patients in process with the intern or interns, okay? In a linear process then, I can sum up the inventory at every step, and that's going to tell me the average inventory in the total process. So I add 20 plus 5 plus 30 plus 15, which tells me that on average there are 70 people in this process, okay? And in a linear process, I can sum up the time at each of those steps, and that's going to tell me the average time in that process. So 1 plus 0.25 plus 1.5 plus 0.75 says that it's 3.5 hours in that process, okay? So let's do a second example. And we're going to add a few steps in here, okay? And so the patient checks in. We know that that takes 5 minutes. They wait, and we say that we have 2 patients waiting. The initial doctor consult takes 12 minutes. The doctor requests tests for the patient. That step takes 5 minutes. they wait for the results of the test, and you have on average one patient waiting there, and then the nurse takes the tests, and that takes about 30 minutes. Okay? And our throughput is 4 patients per hour, right? And so again, I want to transfer the information that I know into a table. So I'm going to take these steps of the process, right? And I'm going to enter them into the left-hand side of the table. So patient checks in, wait, doctor consult, doctor requests tests, we wait again, and then the nurse takes the tests. Okay? So the first thing I do is just put those steps over here. And then I know, again, it's a linear process. So I'm going to input 4 patients per hour across all of the steps, right? And I know I have 2 patients waiting. And then I know that I have 1 patient waiting here at the end of the process. And I have 5 minutes at patient check-in for how much activity time that takes, 12 minutes at doctor consult, 5 minutes to request a test, and 30 minutes to take those tests. Okay? But the problem with this one is that I have 2 different units of measure, right? My throughput is 4 patients per hour, and my flow time is in minutes. So I have to convert them to be in the same unit of measure. Okay? And so typically what I do is I add a column to my throughput, and I convert 4 patients per hour, and I divide it by 60 minutes in order to get how many patients per minute. Okay?
Couldn't you do like 1 patient every 15 minutes? Because it says 4 per hour.
Right? So if you divide it by 1 by 15, I'm thinking you're going to get 0.0667.
So I meant like an hour divided by 4, and then just put it in the minutes.
So that's what you're doing here. So I think there's probably more than one way to get there. Okay? But the bottom line is you want to convert that to minutes. Okay? Because you're saying 1 patient every 15 minutes, right? So now that you've converted it to minutes, right, then you can again fill in the blanks. And so the purple is, well, if I need to fill in inventory, it's throughput times flow time. So 5 times 0.0667 gives me 0.3335. Okay. Again, anytime I fill in the inventory, it's throughput times flow time. So 0.0667 times 12 gives me 0.8004. And so you just keep continuing to fill in the blanks, right? So not hard when we've got the formulas up here. And at the end of the day, again, because this is a linear process, I can sum up all of the inventory, and that gives me the total amount of inventory in the system. And I can sum up all of the flow time, and that's going to tell me on average how long people spend in the total system. Okay? So here's our totals. We have, all right, so if the questions are, on average, how many patients are within the process boundaries at any given time? So Kelly, I'm going to ask you that. On average, how many patients are within the process boundaries at any given time? Do you know?
6.4684. Was that the answer?
You got it. It is. It is. Okay. Eric, on average, what's the throughput for the process?
4 patients per hour.
Right. So that just stays consistent. Sometimes people get to that point and they want to add up the 4 across every step, and that's not the case. It's 4 patients per hour. And then Katie, how long do patients spend in the process on average?
96 minutes.
Right. 96.9775 minutes. Okay. Or we could look at only one portion of the process. So Kelly, if we were going to say, how long does it take before a patient sees the doctor, right? So we'd have to identify what steps before the patient sees the doctor. So what steps would we have to be looking at?
Would you look at the check-in, the wait?
Yep. And then we'd say the doctor's there at the doctor consult. So we'd look at those first 2 steps, right? And we would say they spend 5 minutes at patient check-in plus 29.985 minutes waiting, right? So we total up those 2, right? And so we'd say that they spend on average 35 minutes waiting to see the doctor, okay? Right, so that's the thing. It's the first few problems with Little's Law are just going to be about creating the table and starting to understand how you can break it down into smaller pieces. And then we'll start looking for improvement, right? That's where we are going to head down the road is, okay, now that we can figure out how to look at this information, how can we identify where we would want to see improvement? Okay. Another piece of this puzzle is using Little's Law to analyze financial flows. And so the example that we're going to use is our business process flow paradigm can be used on these financial flows. And if you have income statement, balance sheet, and a detailed cost of goods sold, which for any public organization, you can get that information, right? So again, if we have income statement, balance sheet, and a detailed cost of goods sold, okay? And so our objective is going to be to determine how long it takes for a cost dollar to be converted into revenue for the organization. And so for that, we need a picture of process-wide cash flows, okay? All right, so we have an inventory statement and a cost of goods sold, okay? And so if you think about the measures that we're going to use. So when we talk about inventory, and these are in dollars, right? And so I think, if I remember right, we're talking about millions of dollars here. So let's say that we have $6.5 million in raw material inventory in a roof, okay? So that's saying dollars, it's a snapshot of dollars. So are we talking about inventory, throughput, or flow time?
Snapshot of dollars?
Mm-hmm. So we're talking about inventory, right? When we talk about cost of goods sold, we're talking about, let's take a look at raw materials. So we're saying $50.1 million per year. Inventory, throughput, or flow time? Eric, what do you think? Throughput, because we are talking about dollars per year, right? Okay. All right. So it's kind of important that you remember what unit of measure you're talking about when we start looking at these different areas of financial statements. So when we're talking about inventory, we're only talking about dollars, and it's a snapshot of dollars at a given time, okay? So that makes it inventory. When we're talking about cost of goods sold, we're talking about dollars per year, and so that's going to be a throughput rate, okay? And so if we wanted to then take a look at this, I'm going to come back to this for a second, okay? If we wanted to look at this, we could draw our boundary, we could draw our rectangle around the process, right, from the time that dollars come in to the time that they go out, okay? And again, we're talking about cost dollars, okay? And we kind of break our information into both cost dollars for inventory that's coming in, the parts that are coming in, and cost dollars for labor, okay? And so we would say inside our box, we put the amount of inventory that we have, and our total amount of inventory, if we add up across all of these areas, is 50.6 million, right? And if we looked at the cost of goods sold of parts coming into the system, we'd add up the raw materials at 50.1 and the purchase parts of 40.2. We were going to talk about the labor dollars going into the system. We'd say 60.2 and 25.3, right? And so if we look at how we draw that, we have our parts coming into the system here. So we have 50.1 million per year in raw materials, 40.2 million per year in parts. Labor is 60.2 million per year, and assembly is 25.3 million per year. And what that says is when we add up those four areas, right, that says $175.8 million per year exiting the process. So we're saying that we have this balanced process. Okay? If I want to know how much time a dollar spent in the system, right, my time, we know from Little's Law, I can calculate by inventory divided by throughput. So I can take 50.6 million in inventory and divide it by that throughput of $175.8 million, right? And it's going to tell me that it's in the system for, I thought I had it on here and I don't, for 14.97 weeks by the time I convert that into weeks. So, so in other words, the average dollar invested in the factory spends roughly 15 weeks before it leaves the process through the door of the finished goods inventory warehouse. Could be important to know. If you were comparing your company to other companies in the same industry and you had access to their financial statements, you could see how well your company compares from converting a cost dollar to other companies, right? Could be something that's interesting, okay? However, that's not the whole story, right? So we have this is the manufacturing process, but we also have accounts receivable and accounts payable, right? And that's going to affect, because if I have accounts payable that are outstanding for 9 weeks, right, then I'm actually not, I don't have to, that's a benefit to my converting a dollar, right, because I'm not spending that money early. Or if I have accounts receivable that are outstanding for 9 weeks, that's not such a good thing because I'm not collecting money from people for 9 weeks. So I have to look at both of those two things as well. Okay, so to do that, we go to the consolidated statement of income and retained earnings. Okay, so from that statement, we can find accounts receivable. She says as though she can find accounts receivable.
It's on the next slide.
Oh, no, we can find the throughput for accounts receivable. The throughput for accounts receivable. So what would be the number that would represent how much we bill to our customers every year?
About 47.
Okay, so we've got a couple of different answers there. So if I have total sales of $250 million, I probably have to bill all of that to my customers, right? So we want to go to that bigger picture item, okay? Don't feel bad. I'm not doing this to make you feel bad because I'm telling you, the first time I went through this, I had to think a little harder about it. And then after you go through it a couple times, you're like, well, yeah, that makes sense, right? So the $250 million is what we would say was our throughput for accounts receivable. And then on the balance sheet, right, we can find the snapshot in time of what our accounts receivable actually is, okay? So our snapshot in time for accounts receivable says 27.9 million, right? And so that being said, I can find the average time that a dollar spends in accounts receivable by dividing my inventory by the throughput. So 27.9 million divided by 250 million per year, okay? And I can also determine the accounts payable from here. And so if we were going to look for accounts payable, it's down here all the way in the bottom. It says payables, 11.9 million. What is that payables? What's it going? What would you think it's going to go towards? Any ideas about what we might say that's going to go towards? How about if we looked at our cost of goods sold? Who am I going to owe money to that would be vendors? People that I buy raw materials from and people that I buy purchase parts from. So I can take those two and add them up and get my cost of goods sold for accounts payable. Okay. So if that's the case, right, I can set up my drawing for accounts receivable. I have 250 million per year throughput. I have 27.9 million in inventory, right? And that gives me 0.112 of a year times 52 weeks per year, right? Which tells me it's 5.8 weeks that I have that a dollar spends on average in accounts receivable. In accounts payable, we get that throughput by adding together the purchase parts, right? The raw materials and the purchase parts that we bought for 90.3 million. Our accounts payable was 11.9 million. And when we do the math on that, inventory divided by throughput, it tells us that we have $1 in accounts payable for 6.9 weeks. So at the end of the day, when we want to understand what our cash flow is, right, we say that we have $1 spends 15 weeks in production. It spends 5.8 weeks in accounts receivable. So those are adds, right? 15 weeks in production plus 5.8 weeks in accounts receivable. But then I subtract off the amount that I'm not paying my vendors for, right? So then I subtract off the 6.9. So that says that my cash-to-cash cycle time is 14.1 weeks, right? And again, in a larger business perspective, that's an important number, right? If you could improve that by 2 weeks, that could have some meaning, okay? All right. So let's talk about some different cash-to-cash cycle times. And this is outdated, and it's a little small up there, but let me give you some ideas. So the industry, pharmaceuticals and chemicals, the best in class has cash-to-cash cycle times of 31.3 weeks. The average in the industry is 120 weeks. Tell me if that doesn't make a difference in how a business operates, right? For computers, the best in class was 27.5 weeks. The average was 62.1 weeks. The median was 51 weeks. That makes a difference, okay? Let's do electronic equipment. Best in class was 31.6 weeks. The average was 116 weeks. It's like 2 years from the time that you invest $1 until you recoup it from your customer, okay? And then the median on that was 103 weeks, okay? So you can tell you've got some long investment time, right? And so if you can figure out how to reduce that and turn your cash over quicker, that could be a fairly significant piece of information or a good approach, okay? But the question is, how do you know where to target, right? So now we've said, yeah, we're long, but what does that mean, okay? Well, we want to use this information that we have to make some informed decisions about where we want to target our efforts, okay? And so what we do is we break down the information that we do know. We know that we have 50.1 million per year coming in terms of raw materials. We have inventory of 6.5 million in raw materials, right? For the roof, in terms of fabrication, we have 15.1 million in inventory. Okay, and this information is all coming back from, let me go back to here, right? So it's coming off of some of these financial statements. Okay? So the throughput is listed on the arrows, right? And so when you work your process, I want you to show the throughput like that. So show it on the arrow as you're describing your process. And then the amount of inventory at that location is shown inside the box, okay? Right, so we have 6.5 million at raw materials, 15.1 million at fabrication, right? 8.6 million in inventory at purchased parts. And again, our throughput is 40.2 million up to this point, and then we add it to our throughput that we have 50.1 million per year coming in for raw materials. We have 60.2 coming in for labor, right? And then another 25.3 coming in for labor here. So if you remember, we had our parts set up on this side and our labor set up here. This is going to be one, it's interesting, but you're probably going to have to spend a little bit of time going back to the text and looking at it and looking at the statements to see where it comes from. But so spend time to understand how they developed this chart, okay? But then we get this, we can put in how much inventory we have and what the throughput is, and we can get the flow time for each of these steps, right? Because we had 2 out of 3 pieces of information. We had inventory and throughput for raw materials, fabrication, purchase parts, assembly, finished goods, and accounts receivable, okay? And so if I have that information, then I know that $1 spends 6.75 weeks in raw materials, 7.12 weeks in fabrication, 11.12 weeks in purchase parts, 3.14 weeks in assembly, 2.9 weeks in finished goods, and 5.8 weeks in accounts receivable. So I really want you to make that connection between I can get both inventory and throughput from the financial statements that we have available to us, and then I can translate that into flow time, okay? And the trouble is, that's interesting, but it can also, we can actually get a little bit more information if we chart that. And so our chart is going to say, what's the dollars per week that it spends in each of those areas, and what are the number of weeks that it actually spends in those areas. So what I would say is, if you could make a 1-week improvement in accounts receivable, right, you're talking about $5 million a week that you would actually make available to the company, right? Does that seem like that's important? I think if it were your money, it would feel important, right? On the other hand, and so you kind of look for the low-hanging fruit, right? And so you'd say, well, that's the biggest bang for the buck if we went after accounts receivable. What other way could you look at that? What other one looks like it would have a good opportunity to maybe make some improvement? Any ideas? So we've got purchase parts, raw materials, fabrication, assembly, finished goods, and accounts receivable. So if I look at this axis, it's accounts receivable. What if I look at this axis?
Purchase parts.
Purchase parts, because I have 11.12 weeks there, right? And if I could make an improvement of 2 weeks, it would be close to $1.5 million, right? And so, do you see how you can start to frame this up and say, where do we want to make some focused improvements? And so part of what I want to convey to you is, when you go out and you're working in a position, being able to organize your information and share it in such a way so you can tell someone why it's important that we work on this particular area, right? This kind of information is going to help you do that, okay? And it's important here, big picture, because we're talking about company-wide, but even as you look at a particular process and you start to break down where you're spending the most time in particular steps of the process, you're going to find the bottleneck of the process, and you're going to say, oh, that's where we have to focus our time. Because if you're working on something other than a bottleneck of the process, right, you're not really improving the speed of the process, because it's still only going to be able to run as fast as its slowest portion. So that's why it's a little bit different when we're talking about company-wide, but you can still see where it's important based on the amount of weeks that a dollar spends in those areas. But I want you to make that connection in terms of how that comes together. Okay? All right. And again, I think it's looking at those two axes and saying, on one axis I can see dollars per week. What's my highest dollar per week? And we call that the low-hanging fruit, right? Should be the easiest one to make an impact on. And on the other, it's going to be, well, how many weeks does it actually spend there? All right. So I wanted to go on to an example. And so we're going to do problem 3.3 from the text on page 76. So checking accounts at a local bank carrying an average balance of $3,000. Inventory, throughput, or flow time. Inventory. The bank turns over its balance 6 times per year. On average, how many dollars flow through the bank each month? Okay. So one of the questions I would want you to answer is, well, what information is it asking for you to solve, and what information do you have? Okay. And can you identify 2 out of the 3 components of Little's Law with this information? All right. Well, how many dollars flow through the bank each month says that we're trying to solve for throughput. Everybody agree with that? So it probably means that we have inventory and flow time. Well, we know inventory is $3,000, and if it turns over its bank balance 6 times per year, right, we should be able to get our flow time from that. So we would say then that 1/6 of a year is every 2 months, right? So that's how we're going to convert that inventory turns into flow time. So flow time is equal to 1 over your inventory turns. That's one of the relationships that they share with us in this chapter. So now that I know I have $3,000 in inventory and 2 months is my flow time, I can calculate throughput by taking inventory divided by flow time. So $3,000 divided by 2 months is $1,500 per month. Okay? All right. Then we want to work on another problem, 3.1.1 from page 78 of the text, right? And it says ABC's Corporation's consolidated income statement and balance sheet for 2011 and 2012 are shown below. I have them on the next slide. How do you think cash flow performance in 2011 compares with that of 2012 in the factory as well as in accounts receivable? And do you think that 2012 is an improvement over 2011, and is why? So what they're basically asking us to do is calculate how long a dollar spends in the factory and how long a dollar spends in accounts receivable, right? Which is what we've just done. Okay, so here's our statements. We have net revenues, cost of goods sold, cash, inventories, and accounts receivable. Okay? So, if I needed to know factory flow time, okay? And so factory flow time do you think that you're dealing with a cost dollar or a sales dollar typically when you talk about factory flow time? Mm-hmm. Mm-hmm. Okay, so if that's the case, and we know that flow time is inventory divided by throughput. For the year 2011, what's the inventory that I would use? Can you read it from there, Eric? Yep. Yep. So inventory is going to be 20,880, right? And if our throughput is a cost dollar, we're going to use throughput of cost of goods sold. So for 97,380, right? And that's going to be, if I make that division, 0.2144 years, okay? All right. And then, and I'm sorry, I don't have a slide that really details this, so I'll just kind of walk you through it. And you may want to make a note to go back to that problem 311 on page 78, okay? And then, though, if I said accounts receivable, am I now dealing with cost dollar or sales dollar? Sales dollar, right? Because sales dollar is the total amount you're going to bill the customer. Cost dollar is going to be the amount that you actually pay for your material, right? And so when we talk about accounts receivable, we want the total amount that we're going to bill the customer. So for 2011, my inventory is going to be the accounts receivable amount of $21,596, and I'm going to divide that by the net revenues from that year, right, of $99,621, and that's 0.2168 of a year. I always like to convert that to weeks. I didn't here, but that, so factory flow time in 2011 was 0.2144 of a year, and accounts receivable was 0.2168 of a year. And when I do it for 2012, I'm going to take the inventory for 25,200 and divide it by my cost of goods sold for my factory flow time, right? So 25,200 divided by 98,350 tells me that that's 0.2562 of a year. Okay, so 2011, my factory flow time was 0.2144 of a year, and in 2012, it's 0.2562 of a year. Is my performance improved or disimproved? Disimproved, right? However, if I look at accounts receivable in 2012, my balance is 22,872, but my total throughput in net revenues is 110,644. And so that's 0.2067. So I would say then my accounts receivable has improved, right? So I wouldn't necessarily, my initial question has to go to the factory and say, what's happened between 2011 and 2012? Why are we worse now than what we were a year ago? And there can be legitimate reasons for that, but it doesn't make a lot of sense to try to go beat up on accounts receivable and tell them they're not doing their job, right, when they've improved one year over the next. Okay? And I think you'll find as we go through this, sometimes that can happen. People are looking at a larger picture number, and they can get really frustrated because it's disimproved. But unless you break it down and identify where that disimprovement actually occurred, it's hard to get through. Okay, so I believe that's it for that. Okay, so let's spend just another quick minute talking about what's headed your way then. She says as though she can get there. All right. Got the calendar coming up just so we can it's chugging over here. So let's go ahead and flip out to September. Okay, so you have then the 3B homework, which is going to be similar to the examples that we went over today, is going to be due next Monday night at midnight. I would have extended that out, but because we've got the exam coming up, I kind of need you to go ahead and get it done before then. So otherwise, I'd have tried not to make it due on that night. So, but again, if you slip out now and go get that done, it should be pretty fresh in your memory about the kinds of examples that we use. And then we'll do the same thing then on Thursday. We've got some examples that we're going to go over. And you need to be thinking about what process you want to use, because that's going to also be due next week. So I'm not as tight on that identify the process, but in terms of if you've got an idea and you want to run it by me, try to do that this week, and we'll talk about what may or may not work. I think that that's going to be important. I say that, but then I also try not to let myself get too flexible with the due dates, because then that was a complete disaster there a year ago when I did that. So make sure that you kind of stay on target with that. And we'll do an exam review on Tuesday, a week from today, so that you have a really good idea of what types of problems, and they're going to be mirror image of what you're doing in the homework. So I don't try to create new problems for you to have to apply your knowledge in new ways. I feel like it's enough that you get, I want to make sure that you get the foundation and you can apply what we're learning, and then you're going to apply what we're learning to your project. Okay. Do you have any questions for me? Nope. Does the pace of the class seem okay for you? So far, so good. Kelly, is it working out okay for you?
Yes.
Okay, good, good. All right, well, that being said, I'm going to go ahead and turn you loose, and we'll come back on Thursday and do our third lecture in Chapter 3, and I will see you then.
The conference is about to end.